All right. Good afternoon, everybody. My name is Nick Valentino. I'm an academic counselor in the Hagem Dean's office. I've been working with Dean Paul Funkenbush to present the Full Spectrum series, which is a series of talks or lectures about each of the majors in the Hagem School. We're also going to do a session on data science and material science. So what we want is the opportunity for university students, undergraduates, to be able to consider whether or not they're interested in potentially changing into one of these majors, in this case, chemical engineering, or people from the university community that just want to know what's going on in Hagem School, or people are just interested in learning more about chemical engineering. This is our final session of the week. Next week on Wednesday from 1 to 2, we will be having biomedical engineering with Dr. Edward Brown. And on Friday from 2 to 3, we are going to have the Institute of Optics with Dr. Thomas Brown. So we know a lot of you won't be able to make it. That's why we're posting these on Facebook afterwards, so you can visit, so you can view them or review them again, just so that you have these resources going forward if you decide to learn more about chemical engineering in this case. So today we have Dr. Marc Porosoff, who is a chemical engineering professor. Dr. Porosoff has been very gracious in doing this over the summer and again this fall. So thank you very much. And I'm going to turn it over to you now. And as I said, if you have questions, please feel free to ask or put them in the chat. I will be monitoring the chat. I'm also going to ask if you want to submit your email so we can see we do have some prizes to give away. So I will do that and I will turn it over to Dr. Porosoff. Thank you.
All right. Thank you very much, Nick, for the nice intro. And just so you all note, the way that I do my lectures is I have my video coming through a different feed than the audio. It's just it seems a little odd, but for whatever reason, when I try to have the audio go through my laptop with the video feed, I get an echo that I can't seem to get rid of. So this way seems to work well enough. So you can put me talking in one corner, you can put the slides in another corner to be able to see everything. So I'm going to be talking to you about chemical engineering and giving you an introduction into chemical engineering and telling you what we do as chemical engineers, how they approach problems, what you can do with the degree. So chemical engineering is really a great degree for undergraduate education in engineering because it gives you a background on solving problems, and that's recognized well throughout industry, throughout academia. And it's not it's not a degree that kind of pigeonholes you in a field. You can go off with a chemical engineering degree and go into industry for petroleum companies, pharmaceutical companies. For example, my brother works for Bayer, and he's really in charge of manufacturing of a drug for hemophiliacs. I'm here at University of Rochester, working in chemical engineering and catalysis. You can be a chemical engineer. I have a friend who became a lawyer. You can become a doctor. The options are wide open. It's a degree that really gives you a nice foundation and again, doesn't kind of pigeonhole you in a specific career. You can go straight out of undergrad and get a job. You don't necessarily have to go to grad school. So can anyone name a chemical engineer other than me, which is the answer that I get to this question all the time. And it makes me laugh, and it probably will make me laugh into the future. But if anyone can name another chemical engineer other than myself, if you can think of one. If you can't, that's okay. I have two examples here. So one, probably the most famous one there is Xi Jinping, the president of the People's Republic of China. He's a very famous chemical engineer. Another one is Dolph Lundgren. You might know him better as Ivan Drago from the Rocky movies. I think he's going through some kind of image transformation these days, but another famous chemical engineer. So a little background on chemical engineering is really what is chemical engineering. So what we do as chemical engineers is we apply basic sciences to raw materials to make value-added products. So for example, most classic chemical engineering, crude oil refining into gasoline, kerosene monomers. So the global GDP, 1/3 of the global GDP is involved in a catalytic process. And that has to do with the fact that crude oil and the petroleum industry is such a large industry that is really foundational to our way of life and to our global economy. Other examples are making larger polymers. So we've converted crude oil into small molecules like ethylene, and then taking that ethylene, building it up into larger polymers so we can make things like this plastic water bottle, this whiteboard. I mean, if you can take any object today, this Apple Pencil has plastic in it, has integrated circuits, and it really, any object you can find in your life, chemical engineering is involved in one way or another. These masks we're all wearing, the fibers that go in to make the mask, those are made from polymer strands, classic chemical engineering. So it's all around us in everyday life, and chemical engineering is all about how we can use reactions, catalysts, separation, all these fundamental science concepts and apply them to the real world to improve humanity. So there's some misconceptions around what chemical engineers are, and they're not a chemist who works in manufacturing or an engineer who works in a chemical setting. My least favorite definition of a chemical engineer is an engineer, or is someone who engineers chemicals. That's kind of a meaningless statement that uses the term in the definition. So it's really not an easy profession to enter. It's one of the most probably rigorous degrees at U of R in terms of the number of credit hours that you have to complete in order to complete the degree. And the junior year, once you've completed all of those base level required courses, and now you've become trapped in chemical engineering, is when we throw the really intense chemical engineering courses at you in your junior year, when you're taking thermo and transport and kinetics and really getting deep into the major. But we have a couple of really top students here with us today, and they can answer some questions if you have any about the major. But it's really a great major that constantly exposes you to problems that impact the real world. So there are some key differences between chemical engineering and chemistry. And I think the biggest difference is the scale. So if we look, for chemists, the scale is from vials to beakers, involved with discovering fundamental laws. Chemical engineering, we're much more interested in applying these chemistry concepts and using them in a larger scale, not necessarily a bigger scale, but from a wider range. So chemical engineers can work on a scale as small as atoms and a scale as large as big oil refineries, like maybe you've seen if you've driven up and down the Jersey Turnpike, or you live on the Gulf Coast in Texas. You've seen these big oil refineries, this big equipment. That's very classic chemical engineering. So but it's still important that we have collaboration between the disciplines, because a chemist could discover some drug that's, let's say, really effective against treating COVID-19, but they don't know how to scale this up and manufacture enough doses so everyone can get some. So that's where a chemical engineer can come in and say, well, actually, we have a process. Maybe we can scale this up and figure out how to make this drug on a larger scale. And so chemical engineers are really present everywhere in modern society, from integrated circuits to manufacturing drugs to making solar panels. This one in the bottom right corner, the OLED TV. The OLED was actually invented by Ching Tang, who was a former professor here in the chemical engineering department at University of Rochester. He invented the OLED during his time over at Kodak, and now we see OLED displays are absolutely everywhere. And so we talked a little bit about oil in the beginning and oil refining. So the first oil well was in Pennsylvania in 1857, and we see it's like this very rudimentary wooden structure. And now we have much more modern and advanced equipment for refining oil. So we went from this wooden well to all this fancy equipment we see here in the diagram, where you can see the big distillation columns. And the oil refining as of 2011 was the world's largest industry, about 11 trillion per year. So what we're trying to do now is, instead of drilling into the ground for oil and the environmental burden associated with burning fossil fuels and emitting harmful pollutants into the atmosphere, the question is, can we take a different feedstock, so maybe plant seeds, algae, animal fat, waste cellulose, and process these raw materials into the same chemicals and fuels that we use today, but keeping in mind chemical engineering principles to be able to do that type of transformation. So really, it's the same idea, taking a raw material, but instead of crude oil, we'll take something like cellulose. And can we apply the fundamentals of chemical engineering, transport, thermo, kinetics, reactor design, separations, etc., to be able to process these raw materials into useful chemicals and fuels. And so if we look at the energy landscape of the United States in 2016, what we have here is called a Sankey diagram. So on the left is the different type of primary energy carrier in the United States, and that number below it tells us how much of that energy source we produce per year. So these figures are from 2016, and we see we made 0.5 quads, so 0.5 times 10 to the 15th BTU of solar energy, whereas natural gas, coal, petroleum really dominate our energy scene, where more than, or roughly about 3/4 of all our energy comes from fossil fuels. And so replacing those fossil fuels with some renewables is really an important area of research to see if we can get away from some of those pollutants in the form of CO2 and sulfur and nitrogen, NOx and SOx that pollute our atmosphere. And we're also directly tied in chemical engineering to the grand challenges. And I've circled a couple of the ones that really directly apply to chemical engineering that some of the undergraduate curriculum here could give you an into that area, whether it's through research or through your education that you then go on to grad school or into industry. And one of them that I'll talk about in a little more detail is advancing clean energy, because that's really an interest of mine personally, and one that I think can have a huge impact on the world with a chemical engineering degree. So we see in the past that chemical engineers have done really well with refining, making synthetic liquid fuels, making biofuels like bioethanol, which is now pretty much 10% of all gasoline in the United States, and making electricity from coal or even natural gas. We're very good at that. Those types of power plants are very efficient. But moving into the future, what we're not as good at is making solar and wind as efficient and cost effective as other forms of energy. It's getting better, but still not quite there. Nuclear energy could potentially be a very clean burning fuel if we can safely mitigate the waste. And one that I'll focus on in some more detail today is hydrogen as fuel. And hydrogen as fuel is really interesting. And there was actually an article that came out just this week where Airbus has decided that they're going to try to make these hydrogen powered planes. So instead of powering these planes with jet fuel like JP5, they'd like to be able to fuel the plane with liquid hydrogen. And it's an interesting idea because hydrogen is the best energy carrier in terms of gravimetric energy density. So how much energy there is by weight. Hydrogen is the winner versus anything else. So we see hydrogen is all the way on the right-hand side of this plot. It has a gravimetric energy density of 120 megajoules per kilogram. Compare that with gasoline, which is about 45 or so. So it has more than double the energy density of gasoline on a gravimetric basis. But if we look at this in terms of a volumetric basis, the amount of space that the hydrogen takes up, it's more compared to some of these jet fuels like JP8 up here. So we see hydrogen is better on a gravimetric basis, not quite as good on a volumetric basis. But if you have space in the plane and you design the plane to hold this liquid hydrogen, you're ultimately carrying less weight. You can be more fuel efficient. And when that hydrogen burns, the only product of hydrogen combustion is water. So there's no CO2 or anything harmful produced directly when we burn the fuel. However, you might be thinking, well, where do we get the hydrogen from? How do we make the hydrogen? That's a big challenge in terms of a renewable hydrogen economy. So we've divided this into 3 sections where we have production of hydrogen, distribution of hydrogen, storage of hydrogen. All of these areas need to be addressed before we can move forward and use hydrogen as a widespread energy carrier. So the first is production. We need to be able to make hydrogen so it's carbon neutral. We don't want to, if we emit more CO2 while making hydrogen than we would from just burning gasoline, then what's the point of making hydrogen? Then we need to be able to distribute it around. So a network for distributing hydrogen simply doesn't exist. And typically storage, it's stored at high pressure or as a liquid. And we want to identify if there are ways of storing hydrogen more efficiently. So these are a few of the challenges involved with a hydrogen economy. And before I continue, I just wanted to let you all know that if you have any questions or you have any comments or you'd like to have a question answered, you can feel free to interrupt me, shout it out. I find with these Zoom meetings, it's easier and things the conversation works better if you just interrupt me by posting in the chat box. We'll get to it, but feel free to interrupt at any time. So we'll go through these one by one. So for production of hydrogen, the primary route for making hydrogen today is one of these two routes that I've put the red box around there. So the first is coal gasification, where coal is reacted with a mixture of oxygen and steam. And the other is steam reforming of natural gas, which is a similar reaction to that above that we'll talk about more shortly. And we could look at splitting water, which is just made of hydrogen and oxygen, into its constituent atoms, its constituent molecules, but it's very expensive. So hydrogen made from water splitting costs about $14 a kilogram. And that metric, $14 per kilogram, 1 kilogram of hydrogen contains the same amount of energy as 1 gallon of gasoline. So that would be as if gas prices now were $14 per gallon, would be way too expensive. So the cost of hydrogen from water splitting has to come down to about $3 per kilogram if we want a renewable source of hydrogen that's competitive with our existing energy carriers today. So I highlighted steam reforming of natural gas because this is how about 90 to 95% of all hydrogen is made today. So making hydrogen involves this two-step reaction where we take natural gas that's usually mined through fracking, and we react it with high temperature steam at about 7 to 1100 degrees Celsius to produce hydrogen. And so if we look at this overall reaction scheme, we see two things. The first is that CO2 is a byproduct of this reaction. So whenever we make hydrogen, we're also emitting carbon dioxide. Number two, this reaction is taking place at 700 to 1100 degrees C. And I don't know about you, but I've taken pots of water to boil pasta. You put it on the stove, you turn the thing on high, you come back in 20 minutes and it's still not boiling. And you've used a lot of natural gas or electricity to heat up that water. And for the most part in the United States, most of our electricity comes from coal or natural gas. So effectively, to heat up the reactants to drive this reaction forward, we're burning even more fossil fuels, emitting more CO2 into the atmosphere. So really, although burning hydrogen only makes water when you physically burn it in the plane or let's say in your car for a hydrogen vehicle, you have to think about where did that hydrogen come from? How did we make that hydrogen? And for us right now today, most of that hydrogen comes from steam reforming of natural gas. So it's really not necessarily a clean process for burning hydrogen right now, but as chemical engineers, we're very interested in developing new technology, new catalysts that can make a clean source of hydrogen, because if we had that clean source of hydrogen, it completely changes the energy landscape and CO2 emissions associated with fossil fuels. So one thought is, can we make a device that splits water just when we shine sunlight on it? So we shine sunlight onto an anode, and that causes a reaction to occur, splitting water, making oxygen, making protons, which then combine and are evolved as hydrogen. So a device like this is not really, it doesn't exist today, but in the future, you could imagine that perhaps you could have one of these, let's say at your house, if you had a hydrogen fuel cell car, it just makes hydrogen for you while sitting out the sun, being filled with water, and your car automatically fills itself up, just like a plug-in hybrid. Instead of plugging into the wall, you just get your hydrogen made right then and there for your car in your garage. Another option, instead of doing this through a chemical means with a photoelectrochemical cell, maybe we can make hydrogen biologically. So chemical engineering, there's a whole arm of chemistry that involves bio. And so one thought is maybe we can genetically engineer bacteria, or we can genetically engineer enzymes that when they're exposed to light, air, and CO2 as part of photosynthesis, they also evolve hydrogen. And so could we engineer these enzymes to be faster to make hydrogen at a rate that equals consumption? So that's an area where chemical engineers could certainly impact our world in terms of clean fuel production. I think it's frozen. There we go. And so another area I'd like to talk about is the nitrogen cycle. So that's another grand challenge where chemical engineers are directly involved and where there are plenty of research opportunities emerging today. So the nitrogen cycle is how all plants are alive today, how everything is alive today thanks to the nitrogen cycle. So we need nitrogen. It's integral to making proteins. And the natural cycle is nitrogen in the atmosphere gets fixed into the soil through nitrogen fixing bacteria. And then there's some reactions that occur. The NH3 gets converted to NO3, which can be assimilated directly into the roots of plants. However, this process naturally can't sustain us on Earth. There simply isn't enough nitrogen available in the soil to grow enough food to keep everybody sustained on Earth. If we look at this graph that goes back to 10,000 BC and we just go into more modern times, we see that within the last 100 years or so, the population of the Earth has absolutely exploded and is growing exponentially. And it's thanks to nitrogen-based fertilizer that humanity can be sustained at these population levels. So we see from the 60s or from the 70s when we were at about 20 million tons of nitrogen fertilizer produced per year to closer to today where we're at over 100 million tons of nitrogen fertilizer produced per year. We can then take that population graph and this nitrogen fertilizer consumption graph and put them together. And what we see that in 1900, before we needed nitrogen fertilizer, nobody on the world was sustained by nitrogen-based fertilizer. However, today, 3.2 billion people as of 2008, it's more now, but roughly half of the world's population is sustained by nitrogen-based fertilizer. So that's NH3 production has been absolutely integral. So making ammonia has been integral to keeping the world's population at the level what it is today. Without ammonia, this process that I'm showing here, Haber-Bosch, which is a process that was created by chemical engineers during the First World War. Without this process to make ammonia, the world's population would probably only be around 3.5 billion people instead of the 7 billion that it is today. So this process was created by Haber and Bosch during the World War. There was a blockade in the natural nitrogen deposits that existed in South America that were mined by the Americans and the British. There was a naval blockade. The Germans couldn't access it anymore. So Haber and Bosch were tasked with how can you make ammonia, NH3, from air and water? And so they made hydrogen from methane using steam reforming. They took nitrogen out of the air and they identified catalysts to react these two reactants together to make liquid ammonia, which we then can use in fertilizer. And so the efficiency of this process is greater than 95%. And this is the process that we use today to make ammonia and sustain the planet. And so Haber-Bosch process with making all that ammonia is responsible for about 1 to 2% of all the energy that's consumed worldwide. So a better way to put it might be it's responsible for 1 to 1.5% of all power consumption worldwide. So about 1.5% of all the energy that's created at any time, at any moment in time, goes into making nitrogen-based fertilizer, which is just an absolutely astounding number. But it makes sense because we need this to sustain life on the planet, to sustain all 7 billion people. And without nitrogen-based fertilizer, about half of all ice-free land would be required on the planet to make enough food to sustain life today. And so where do chemical engineers come into play? So chemical engineers identified the initial catalysts that made this process possible. But as we see, it uses so much energy that the thought is now, can't we identify different catalysts, a new process, use our modern technology to be able to figure out ways of bringing down the energy cost for this reaction? So a catalyst, what it does is it lowers the activation barrier for a reaction. And we see that based on this red dotted line. So there's less of a hump that we have to get over, less energy that we need to put in to get this reaction going, where we react nitrogen and hydrogen together. And so there's, if you type into Google Scholar now, ammonia catalyst, and you search for the last, let's say, 2-3 years, you'll find hundreds and hundreds of articles on new catalysts that are being developed for this reaction. But it's a really difficult problem because the current catalyst we use today is just made up of iron and potassium, two of the most abundant and cheapest elements that exist. So there's a very high bar right now that needs to be overcome. But there's a lot of creative thoughts out there, and there's a lot of faculty researching and industry researching new catalysts for this area, because the potential savings on not only energy, but the emissions associated with that energy consumption would have an enormous impact on our planet.
Professor, we have a question.
Yeah.
It says, I am currently on track for a degree in biochemistry, and I was trying to decide whether or not I wanted to double major or completely switch my major to chemical engineering. Using alternative energy as an example, what is the difference between biochemistry and chemical engineering? I understand biochemistry is the study of the biological process with a focus on what is chemically occurring, but I feel like this is pretty close to what chemical engineering is.
Mm-hmm. Yeah, absolutely. So there definitely is a lot of overlap between bioengineering and chemical engineering, so much so that not here at Rochester, but a lot of universities have changed the name of the chemical engineering major to chemical and biomolecular engineering to be more inclusive and accommodate that bio side of the major. It's really more of a marketing problem than anything else, because chemical engineering is classically thought of as oil tankers. We don't really know what you do. Maybe chemical engineers do some like fermentation and distillation and make alcohol and all this stuff, but what exactly do they do? Is it involved with bio? I don't know. But bio is actually one of the major branches of chemical engineering. So if you're interested in energy and bioengineering, the place you probably want to be is looking at things like algae and bioorganisms to see, can we genetically engineer the enzymes in these organisms to be able to make the products that we want? And that's what I think is actually the future of chemical engineering, is instead of doing these processes synthetically and through industry with the existing like thermal catalysis, can we just make organisms that sustain themselves and naturally make the products that we want while living off of what's already out there in the environment? And that would be a huge leap forward from where we are now. But the problem is the catalysts that exist in nature, so the enzymes, are a lot slower than the catalysts we can make synthetically. So there's a big gap that needs to be filled, but you could take that one of two ways. You could say, oh, it's so far behind, they're never going to catch up. Or you could say, this is a big challenge to overcome. I want to be involved in finding the solution. So I hope that answers your question. Okay, so we talked a little bit about ammonia production. And so with this ammonia production at lower temperatures under milder conditions, it would be earth-shattering and certainly Nobel Prize worthy if you developed a device where you fed in air and water, you fed in renewable energy from solar panels or wind turbines, and you used the renewable energy to split water into protons and oxygen. And then you use those protons from water to react them with nitrogen from air to make ammonia. This would be an earth-shattering Nobel Prize winning device if you could develop the technology to make something like this. Right now, it's really more of a pipe dream than anything else to do this on sustainable levels. But I mean, catalysts get better and better over time. Technology gets better and better over time. So in the future, I wouldn't be surprised if a few 10, 15 years down the road, we see that a device like this is able to be competitive commercially with the existing Haber-Bosch process. Another example that we can think of that directly ties in to the question about energy, chemical engineering versus bio can be found in peanuts. And does anyone have a thought of why I've included peanuts here? And if you're in my class, I gave a similar slide on this in the past, so please no cheating if you know the answer already. So any thoughts, what's interesting about peanuts? If you don't have any thoughts, I'll continue on. You can feel free to shout it out. So peanuts are interesting, and all legumes are interesting when it comes to ammonia, because they contain diazotrophs in their roots, which are bacteria that receive organic acids from the peanut roots while supplying ammonia to the peanut plant itself, or the legume plant itself. So these plants can naturally fix ammonia by themselves from the soil and from the air without the need of nitrogen-based fertilizer. And if we look at the enzyme in Diazotrophs that's responsible for making ammonia and breaking apart the nitrogen-nitrogen bond, which is one of the strongest bonds that exists in nature, it's a very strong triple bond. So this cluster of catalytic sites, this iron sulfur, phosphorus, iron molybdenum cofactor, are responsible for performing the enzymatic catalysis for making this ammonia. And maybe we can gain inspiration from nature in designing new catalysts synthetically that are even better than nature at making ammonia. And we see that all the time in catalysis and chemical engineering. It's going to nature for inspiration for what we can do synthetically, perhaps even better than what nature does, because nature's been around for millions of years, subject to evolution. These processes have been refined over time. So they should be pretty good at what they do, and maybe we can use them for inspiration to make our technologies even better. And so if you're interested in these types of problems, why chemical engineering? So chemical engineering, the jobs that exist are really as open as you can imagine if you're interested in math and science. So they're involved in energy efficiency, economics, assessing environmental impact. Chemical engineers typically work with chemists and other scientists for scale up. Like if a chemist invents a specific drug, chemical engineers can help scale it up. Chemical engineers make excellent managers. So if you're interested in being a boss and leading teams, it's a great degree for you. And chemical engineers can provide technical expertise to customers. So if you work in a company that makes a particular device, you could be the chemical engineer on call that interfaces with the customer to say how it works and how to solve their problems. And so chemistry and math, I would include physics here, are critical for chemical engineering. They're foundational to the major, and that's why the first 2 years is really heavy with the prerequisites, chemistry, math, and physics. If you like solving tangible problems, chemical engineering is a great major because you see how the theoretical concepts of these basic science and math courses are applied to solving real world problems. And a lot of chemical engineering, you're making real things. So I have a chemical engineering friend who I've known for many years. We met at conferences while I was in grad school. He now works for this company called Apeel, and they're developing a coating that they're applying to different fruits and vegetables that make their shelf lives longer. And it's a completely safe coating. They've got all kinds of funding from venture capitalists. So this is an example, like if you have an idea, you want to make a new material, you want to scale it up and make it real, with a chemical engineering degree, that's absolutely something you can do. And so at U of R, our vision is to achieve global research recognition in clean energy, sustainability, and biotechnology, providing outstanding education at all levels. So our goals are, number one, research. We have good relationships with LLE and the Med Center. We pride ourselves in our graduate education by offering master's and PhD degrees in addition to our undergraduate bachelor's degree. We've we really have a strong focus on undergraduate education and making that experience as good as possible, and have good relationships with local and national other institutions and industry. So we'll help you find a job and get into a nice grad school. So my undergraduate students who were working with me in my research lab who graduated last year, one of them is at Penn State doing a PhD in chemistry. Another is at Notre Dame, also doing a PhD in chemical engineering. So our students find good homes after graduation. And to give you just a snapshot of chemistry at U of R, here's just some boilerplate information, our number of undergrads, grad students, number of faculty. We're currently at 11 tenure track faculty. We have a couple of instructional faculty, and we have all the administrative staff you need for whatever questions to help you get through your undergraduate curriculum. And so research opportunities, we very much too encourage that undergrads get involved in research. I'd say a good time is probably maybe middle of your sophomore year. It can be tricky during your first year. There's so many things going on. With the pandemic, it makes it even more difficult to get the undergraduates directly into the laboratory these days. But as we progress, as the situation gets a little bit better into your second year, I would definitely recommend getting involved in research. And you can do this through directly here at U of R. There are REU programs at other universities. We here have the Eisenberg Summer Internship Program. It's a competitive program for chemistry majors to participate in paid summer research with U of R chemistry faculty. If there's a faculty member you're interested in their research, I recommend the first thing you do, go on their website, see what they're doing. The second thing you do is try to find recent publications by them, because faculty are notoriously terrible at updating their research websites. So if you want to know what they're up to right now, type them into Google Scholar or Web of Science and see what papers they've published within the last couple of years, because you might find a faculty member, oh, their research looks really interesting. I want to work in their lab, and it turns out they haven't been research active for 10 years and they teach now. So you don't want to waste your time putting in effort where that's going to get you nowhere. So start off, look at the websites, kind of see who you're interested in. Then you want to see who's publishing papers and who's research active. And they can really and then you can go ahead and reach out and send an email. And when you send emails as an undergrad, you want to make yourself available. You want to make it seem like you've done your homework. You want to list a few times, this is when I can meet, and try to ask some questions and keep the conversation going. It can be really difficult to get into research labs, but above all, the most important thing is you want to appear serious, invested, and mature in how you approach the faculty members. And sometimes maybe things won't work out. The lab is full, like right now. I'm having a hard time getting all the undergraduates who want to be involved in research, but we're doing the best we can to keep things going safely. But don't get discouraged, keep following up, be persistent, and try to it's really important to show that you're invested and you want to be involved, and that could help you with finding a research position. So that's really all I had prepared on just kind of general chemical engineering, what you can do with the degree, what we offer you here in UR Chemical Engineering. I really wanted to leave plenty of time for questions. And if you're interested too, I have a little bit about my research that I can talk about afterwards if you'd like. So, but I'm happy to take any questions from the audience. So thank you all for your time and listening.
Do we have any questions we can think of? We can either put them in the chat or we can say them aloud.
Yeah, either way.
Can you talk about the similarities and differences between like environmental engineering and chemical engineering?
Yeah, it's a good question. So I'm not as familiar with environmental engineering, so I can't speak directly to that, but I would say environmental engineering, you're a little more specialized in terms of the problems that you'll solve. So I think you could have a chemical engineer working in a position that was originally designed for an environmental engineer, but you might not be able to have an environmental engineer work in a position that was originally designed for a chemical engineer. So I think chemical engineers have all the tools necessary to solve environmental engineering problems. It's just a matter of what those specific problems are. Those are all going to be related to the environment. So an example might be, well, how do we remove this pollutant from the atmosphere, or is this particulate matter being emitted by this process a problem, and how do we deal with it? Those are problems that chemical engineers are exceptional at. And problems like separations from water. So if water gets contaminated, how bad is the contamination? What's the contamination? How do we mitigate this contamination? Something that an environmental engineer could do, something that a chemical engineer absolutely could do as well. But if it's a problem like, well, I'm not really sure what I want to do, maybe environmental engineering, maybe chemical engineering. One suggestion is that you can do a chemical engineering major with an environmental engineering minor. And that, I think, to fulfill that requirement, it's something like you only need to take 1 or 2 extra courses. So it's very, very doable if that's something you're interested in. But I'm definitely biased. Yeah, you're welcome. I'm definitely biased toward chemical engineering. So I would push chemical engineering over environmental engineering. But you have to talk to the environmental engineers to get their perspective. But I would say it's a little more focused on the type of problems that you'd be solving. They'd be all directly applicable to the environment. Whereas chemical engineering, I think it's a little bit of a broader field. You might not have some of the specializations into the nuances of the problem as a chemical engineer, but that doesn't mean you can't learn them. Like ultimately, a chemical engineering degree teaches you how to think and gives you the foundation that you need to move forward in your future career, which is why it's such a desirable major for employers, and why it's such a versatile degree, and the career options are really open-ended after graduation with a bachelor's.
We've had a request to hear more about your research, and also another question.
Okay.
The question is, how did you develop your interest in catalysis?
So that's a great question. So actually, I really didn't know much at all about catalysis after I finished my undergrad. So I did my undergrad at Johns Hopkins in Baltimore. And when I went there, there was no catalysis program or really energy program at all, except for one professor who was working on biofuels. So we really had almost no exposure to catalysis whatsoever. So during my undergrad, I worked on bio research a little bit, and my master's, we worked on drug delivery for anti-HIV and anti-HSV. But I kind of always had an interest in alternative energy and climate change, because I saw it as, and I still see it as, a silver bullet to many of the world's problems. If we can develop a clean source of energy, a lot of problems that we have today just go away. There are so many problems that can be solved just from clean, renewable fuels and other forms of energy. And what I realized when I went to grad school was catalysis is really at the crux of all of these problems. That for making the new molecules we may want today, like plastic, I don't think is going anywhere. Like it's too important in terms of medical applications. It has such high strength to weight ratio that it's a really excellent versatile material. But can we make plastic that doesn't end up in the ocean to the point where we can't do anything about it? And that's a catalysis chemical engineering question. As is, can we convert CO2 into something more useful and less harmful? Can we do something with it? So catalysis is really directly tied into energy. So if you want to do something more like solar panels, I'd say that's a little bit different. That's off the path of catalysis, but it, in of itself, catalysis gives you a lot of options into what you can do to impact renewable energy. So I hope that was a useful question, a useful answer to your question.
I have a question more about, I guess, your academic path. Can you talk a little bit about your experience as a high school senior going to your first year as an undergrad and your academic choices and how that felt?
Right. So I actually just had this conversation with a student of mine today. And I strongly think U of R should adapt this concept, especially in the world that we're living in today, but that's kind of above my pay grade. But so I finished high school, and it's kind of funny. So I'll tell this story from the very beginning. So I was applying to undergrad and I had my list of schools all made up, and I felt like something was missing from this list. Like I wanted to add another school, but I didn't know which one. And I was browsing through a list of schools and I see Johns Hopkins, and it's like, okay, it's Hopkins. I know they're good at medicine, but they probably have good math and science too. And that's what I'm interested in. So I'm going to throw that name onto the pile. Start getting like acceptances and rejections back from different schools. And I'm going through my email one day in the middle of April, and I see in my junk email, there's a letter like from Johns Hopkins, and in the subject line, it says, congratulations. So I click on it and I find out I got into Hopkins and ultimately ended up going there through an email in my junk email. I got to Hopkins and I knew I was interested in math and science. I was really good at physics in high school. So I was like, I'll be a physics major. That seems like a great idea. And I took physics for physicists my first year and lasted about 2 weeks in that course, and decided that it was way too theoretical and not nearly applied enough. I wanted to do a major that was more applied. So my brother was a chemical engineer, and I learned a little more about chemical engineering and thought, you know what, this is the right fit. It combines math and science. I don't really know what I want to do yet, but it'll set me up for success. So went into chemical engineering, and turned out that first semester really, not knowing what I wanted to do was a mess. I did terribly. My grades were awful. But luckily, Johns Hopkins has covered grades first semester freshman year. So nobody ever saw those grades. I didn't even see those grades. So I'm kind of afraid to look at them, but things worked out okay, I guess. So that's something that I think is really, really beneficial, especially as a first year. And I think U of R would do great to adopt that type of policy,